Hello and welcome to this video lesson on transition metals. This is the first of a series of lessons on the transition metals, and we're going to cover the basics here and then go into some more detail in the subsequent lessons. Okay, we have just two learning objectives for this video lesson, first of which is we want to know that the transition metal characteristics of the elements titanium to copper arise from an incomplete D sublevel. So that's to do with the electronic structure in the atoms or the ions. So the characteristics come from the incomplete D sublevel. And then we also want to know that the characteristics that we're talking about include complex formation, formation of colored ions, catalytic activity, and variable oxidation state. So really when we're talking about these characteristics, we're talking about the chemical characteristics. But let's start off with a definition of transition metals, because it might surprise you that the transition metals are not exactly the same as the D block elements. So here we have a periodic table, and you can see the section in the middle called the D block. You'd be familiar with those, and at GCSE you just call them transition metals as an alternative. But actually they are not all transition metals. The transition metals are from titanium through to copper, at least in period 4, and the same down here. So these are transition metals, and these are from scandium downwards and from zinc downwards are not transition metals. They are D block elements but not transition metals, and we'll explain why. We'll explain why with a definition of a transition metal. So a transition metal is a metal that can form one or more stable ions with a partially filled D subshell. So let's just unpick that a little bit for you. So we're talking about ions here. When the ions are formed, they still have a partially filled D subshell. That's what defines a transition metal. So if you take scandium, for example, when it forms ions, it loses its two 4s electrons to form a scandium 2 plus ion, and therefore its D subshell is empty. Right, so it's not a transition metal, even if it is a D block element. And with zinc as well, when zinc forms an ion, you get Zn2 plus, and again the 2 electrons it loses are the 4s electrons. They're the ones that are lost, and it keeps all of its D electrons, so its D subshell is full. So with zinc, the D subshell is full, and with scandium, the D subshell is empty, and therefore they don't have partially filled D subshells like the elements titanium to copper do, and so titanium to copper are the transition elements. So don't worry if you didn't get that straight off, because we're going to spend a whole slide on electronic configurations now. And just a quick reminder before we move on about the little rules you learnt at AS level. So when electrons are filling up sublevels, they fill up the sublevel of the lowest energy first. So lowest energy sublevels first, as we're adding more electrons to an atom. And the other rule, one of the other rules, was that the electrons occupy orbitals singularly before they pair up. Singularly occupy orbitals before they pair. Okay, so there's a couple of our little rules that we learnt at AS. Before we move on, let's give ourselves a little periodic table to refer to in the top corner here. And then we're going to go through the electron configurations of all the transition metals using this chart here. You'll remember that there's a few ways that we can write out electronic configurations, and we've got two of the ways here. On the left hand side of the, with all the yellow boxes, we're going to draw the arrows in the orbitals. Each of the yellow boxes is an orbital, and we have the 3D orbitals here, 5 3D orbitals and the 4s orbitals, because we're going to concentrate on the transition metals of period 4. And we're going to make it easier for ourselves by noting that they all start off with the electronic structure of argon, and we're just going to add 2 argon because that's where we see the differences. So we've got argon plus all these electrons that we're going to write down. There we are. So let's start with the first one, which is titanium. So let's write titanium here. And titanium, of course, is going to start off with its 4s electrons already filled, because calcium has its 2 4s electrons, and then scandium has added 1 electron, and titanium adds the 2nd electron. So that's what the electron configuration of titanium looks like, and we'll just write that in shorthand as well. So we've got 3d2, we've got 2 electrons in our 3d shell, and we've got 4s also filled with our 2 electrons. Then when we move on to vanadium here, these 2 electrons of course stay, right? These 2 electrons stay, and we add a 3rd one in for vanadium. I should have written vanadium up here. So this is vanadium, and so then in the same way we've got 3d3 but still 4s2, because our 4s 2 electrons are lowest energy and they've been filled first, and only when our 4s orbital is filled do we go back and backfill the 3d orbitals. Moving on to chromium. So chromium again has its 2 4s electrons, and then it's adding another one like that. So you would expect chromium to be like that, it's following the same pattern, but as it happens, chromium is an exception, and what it prefers is it prefers 1 electron in each of its 3d orbitals. That gives it more stability. So what happens is one of these 4s electrons moves to the 3d orbital, the empty 3d orbital, so that now we have 6 orbitals, the 5 3d orbitals and the 1 4s orbitals, all with 1 electrons in each one, and that gives chromium more stability. And so we write that 4s1, and of course, we've got 3d5. So moving on to manganese, our electron that had jumped into the spare 3d orbital jumps back into the 4s orbital to follow the same original pattern, and we've got all of our electrons in our 3d orbitals occupying them singularly. And so we go back to 4s2, and we've now got 3d5 still. So our extra electrons come back into the 4s orbital. Okay, so now we are going to deal with iron, and iron is quite easy, just follows the same trend. And so we're going to have 2 electrons in here, and all of the single electrons in each of the orbitals, and one of the next orbital of course has to pair up, and it pairs up in the first 3d orbital, and that was iron. So iron is 4s2, 3d6. And moving on one further to cobalt, start off, and our extra electron goes in our next 3d orbital. These are the electrons already there, so cobalt is 4s2, 3d7. Next one, which one's the next one? Nickel. Nickel's another simple one, just follows the same trend. (4s2), 3d8. And last transition metal in period 4 is copper. And copper is another exception, so let's highlight our exceptions. We had chromium was exception that often appears as an exam question to see if you've understood this, and copper is our other exception. Right, so let's explain. So our copper exception. So first of all, what you would expect if you were following the same trend as we've seen through the rest of the transition metals. So everything's the same as nickel so far, except we get our extra electron there. So that's what you'd expect. But as it happens, in a similar way to chromium, copper actually prefers a full 3d orbital. Well, 5 full 3d orbitals, a full 3d subshell. So what happens is one of these 4s electrons jumps out and occupies a 3d orbital instead, and that is more stable. So for the copper atom to have a full 3d sublevel and a partially filled 4s orbital, it's more stable for it than the original way we drew it. So that's how it exists in nature, and the way that we write it is 3d10 4s1, like that. So while we're on electronic configurations, why don't we explain why scandium and zinc aren't transition metals. So first of all, scandium. Okay, here's scandium here, and scandium would be 4s2 3d1, but when it forms ions, it forms scandium 3+ ions, and so the electrons that it loses are these two, loses these two and the 3d electron. So loses these electrons to make your scandium 3+ ion. So therefore, as an ion, the 3d orbital is empty, and that's what disqualifies it from being called a transition metal, and it's also because of that it doesn't follow the same chemical properties as the others, which do have partially filled 3d orbitals when they form ions. So that was scandium. Let's also do zinc. And the electronic structure of zinc is argon. I should have had argon in here as well, to be honest. So argon, and then it's 3D10 4s2. And when zinc forms an ion, it's these two electrons that are lost, such that the ion becomes Zn2+, zinc 2+ ion, and you can see that the 3D sublevel is full, and that's what disqualifies zinc from being called a transition metal, and it's also what gives it different chemical properties to the transition metals for real. Okay, so now we're going to have a look in a little bit more detail at how transition metals form their ions, because there's an important little anomaly here that we want to be aware of. And so first, let's just remind ourselves that when electrons are added to atoms as you're going through the periodic table, you're going through up by one atomic number to the next one, you're adding electrons. You're adding electrons to the lowest available energy level. So that's our first rule, and in the case of transition metals, that means that the 4s electrons 4s2 have been filled up already, so they're filled up with potassium and calcium, and then you go back to filling the 3D orbitals. The 3D orbitals filled afterwards, and that's because the 3D orbitals are slightly higher energy than the 4s orbital. However, here's the crazy thing. The crazy thing is that when you lose electrons, when you're forming ions, that is, because they're metals, they're going to lose ions, they lose electrons when they form ions. When they lose electrons, it's the 4s electrons that are lost first. So they're not lost in the same order as they are gained. So there we are. And the way that I think about this is that when you're adding electrons, as you go up through the periodic table, you add them to the lowest energy levels first. But when you're losing electrons, you lose them from the orbitals that are furthest away from the nucleus, i.e. the 4s orbital furthest away from nucleus. So instead of losing them from the highest energy level, as you would expect if you're just reversing the trend, instead of losing them from the highest energy level, you actually lose the electrons from the energy level, the orbitals that are furthest from the nucleus. And 4s is further away from the nucleus than the 3D. So they are the electrons that are lost first. Okay, so there's our little anomaly. Well, I'll call it an anomaly. It's a fact. It's a true fact, so it's not really an anomaly, but hopefully you've understood that. And then now what we can do is we can get onto some transition metals. Let's use a periodic table, and let's see if we can squeeze in a couple of examples. So we're going to have a look at iron. First, let's have a look at iron. Let's put iron up here. So iron is argon, first of all. And then it is, let's put 4s up here. So it's 4s1, 4s2 for our potassium and our calcium. And then it is 3D, 1, 2, 3, 4, 5, 6. 3D6, 4s2. Now when iron loses electrons to form an ion, then what happens is we're going to lose these 2 electrons. So we have argon 3d6, and that becomes Fe2+. But iron, as you're probably familiar with, forms not just Fe2+ ions, but also Fe3+ ions. And when it does, it loses, let's switch to purple. So when it does, it loses not only the 2 4s electrons, but also one of the 3d electrons. So it becomes 3d5. No 4s, so we don't write that down, and that is iron 3+. So that's iron and the 2 ions that iron makes. Let's have another example, shall we? So let's say you had an exam question, and the exam question said, what's the electronic config of Mn2+ ions? So that's your exam question, and you have to write out the electronic configuration of manganese ions. So first of all, we're going to find manganese on the periodic table. There it is there. And our first step, just like with iron, is that we would write out the electronic configuration of a manganese atom. And we start off with argon again. And then, as well as argon, we've got our 4s2 electrons in the same way from our calcium and our potassium. And how many 3d electrons have we got? Let's count them again in the same way. We've got 1 for scandium, 2 for titanium, 3 for vanadium, 4 for chromium, and we've got our 5th one for our manganese. So write in a little 5 there. So that's our electronic structure of the manganese atom, and we are asked for the electronic structure of the manganese 2+ ion. So we can quickly see, right, following this rule that we drew in the top right hand corner, that these are the electrons that are going to be lost when it forms an ion. So the manganese 2+ electronic structure is going to be 3d5, but no 4s2. That's what it's going to be. So let's just review where we've got to in our learning objectives. They were our 2 learning objectives, and what we can see is we've spent a lot of time on electron configurations, and the reason is that we need to understand incomplete D sublevels in order to do both of the learning objectives. So we've sort of studied electronic structure in some detail, and so now we can start going on about characteristics of the transition metals to deal with these 2 learning objectives. So firstly, let's think about physical characteristics. They're the easier ones. So the physical properties of the transition metals. What we have here is a bunch of transition metals for you. And what we can say about the physical properties of the transition metals is that they're all pretty similar. So in terms of density, they're all high density. They're all dense metals and all have pretty similar densities to each other. So they're all high densities. And as far as the boiling points are concerned, or melting points, they all have high melting points or boiling points. Some of you might just be thinking about mercury there for a second. Mercury is not actually a transition metal, even though it is a D block element. And the reason why mercury is a liquid at room temperature is way beyond A level. And you have to understand general relativity as it happens before you can get there. Anyway, so all the transition metals that we deal with are high boiling points. And lastly, the atomic radii. The atomic radii are all about the same. They're all more or less the same. As it happens, if you wanted to get into tiny differences, you would see a slight decrease in atomic radii as you went across period 4, because the nuclear charge is increasing and yet you're adding your electrons to the same 3D orbitals, and so that increased nuclear charge slightly attracts those 3D orbitals nearer to the nucleus as you go along the period, but the difference is tiny, and so what we can say is they're all more or less the same. And that's as much as you need to know about the physical properties of the transition metals, because all the work we do is on the chemical properties of the transition metals, which we can deal with now. So all we have to do in this video lesson is to list out the chemical properties that are interesting about the transition metals and arise because of their incomplete D sublevels. So we're just going to list them out, and in subsequent video lessons we're going to go through individual chemical properties. So firstly, they form complex ions. They form complex ions. So if you've not come across these before, have a look at this. In the middle we have an Fe3+ ion, and then attracted to that high density of positive charge are the polar molecules, the polar water molecules, and 6 of them. And if you were interested, you'd find out that these bonds here between the water molecules and the iron 3+ ion are coordinate bonds, and they make a complex, a metal complex, right? That is the formula for which is given at the bottom left-hand corner there. All right, so metal complex ions are a feature of transition metals because of their high positive charge density, attracting polar molecules that they're swimming around with. That's the first one. The second one is that they form coloured solutions when they're dissolved. So for example, if we're sticking with iron, iron 2+ is a pale green colour, whereas iron 3+ is a yellow colour. And there you can see that the colours of various other different transition metal ion solutions. So they form colours, and that's also because of their incomplete D subshells. So thirdly, they act as catalysts, and I've given you a energy diagram here where with a high activation energy without a catalyst and a lower activation energy for the pathway with a catalyst. And transition metals are often used as catalysts. So for example, iron is used in the Haber process, you'll remember. So they're good catalysts, and that's also down to the fact that they have incomplete D sublevel when they form ions. And lastly, a fourth chemical property that we are going to become familiar with is variable oxidation state. Okay, so we have our transition metals here, and scandium across and zinc are D block but not transition metals. And you see, for all of the transition metals we have these +2, +3, etc. oxidation states. So these are all the oxidation states. Oxidation numbers. And so take an iron, for example. Not only is it existing as +2 commonly, and also highlighted there is the color, that little sort of pale green color, and our iron 3+ ion is a yellow color. So it exists as those two ions, and also +4, +5, +6, rarely, but they do exist. And the same for the other transition metals, exist in various oxidation states. And that, in fact, is what enables them to be such good catalysts, but that's for another video lesson. And just to highlight this difference, let's take our zinc and our scandium, and you can see they don't have variable oxidation states. They don't form complexes. And they don't form coloured ions, coloured solutions. And that's because they don't have their incomplete D sublevel when they form ions. So there we have it. But before we finish, let's just check that we've covered off our learning objectives. So now we studied electronic configuration of transition metals and saw that they have incomplete D sublevels in both their atoms and their ions, and that's what gives them their characteristics. And those characteristics are, they form complexes, like that iron 3+ hydrated complex ion, hydrated with 6 water molecules. They form coloured ions. We saw that Fe2+ was pale green and Fe3+ was yellow. Catalytic activity we're already familiar with, and variable oxidation states. We've done that too. So we can give ourselves a big tick on both of those learning objectives. Thank you very much.